Hello, we're going to talk about, look at 12e Dumois theorem. So Dumois theorem says if you have some complex number, let's say z is equal to r cosine theta plus I sine theta, it says that when you take z to the nth, you're going to get r to the nth power, and then you're going to have cosine n theta plus I sine n theta, right? So it's actually a pretty easy formula, right? So you can just raise to whatever power that is, but then these become the multiple. And you can see that pretty easily. And all you have to do is, let's say what happens when we square this, right? Well, r times r is just going to be r squared. And then you're going to have cosine theta plus I sine theta. You're going to multiply it times itself. Cosine theta plus I sine theta. And then what are you going to get? You still got the r squared. Now let's look what we happen. The real parts, you're going to have cosine squared. And the other real parts of multiplying these two, it's going to be minus sine squared. Maybe you already see what that is, if you notice what that is. Now the complex parts, right? What are we going to get? Well, it's going to be the middle terms, sine times cosine. But then also another sine times cosine, or better yet, I should write it like this. You're going to have 2 sine theta cosine theta, right, as your imaginary parts, right? And what is that going to end up? If you notice, these are our double angle identities, right? And this is going to be cosine 2 theta plus I sine 2 theta, right? So it fits with this formula. And then if you want to see it again, well, let's see, maybe it won't work for the next time because, you know, can't always assume it always works. But you can cube it, right? And you're going to end up taking, if you cube it, you're going to have multiply this by another r cosine I sine, right? So you're going to end up with just r cubed, and then you're going to have cosine 2 theta plus I sine 2 theta that we already had, and then we're going to multiply it by another cosine theta plus I sine theta, right? And now we got the r cubed. Let's see what happens. We're going to have this times this, right? That's our real part's going to be cosine 2 theta plus times cosine theta, right? And the other real parts of this, so it's going to be minus sine 2 theta sine theta, sine 2 theta sine theta, right? I'm going to run out of room. That's my real part. My imaginary part, I'll just write it down here. So I'll have I. What am I going to have for the imaginary part? I'm going to have sine 2 theta cosine 2 theta. So sine 2 theta cosine theta plus the other real parts is cosine 2 theta sine theta. A little messy there, guys, but it's all right. Good. And then there we go. Now, if you notice what we have right here now is the fact that this is our compound. It's cosine, cosine, sine, sine, 2 theta, theta. That's our addition property for our cosine. So that's r cubed. And then we're going to have cosine. What's 2 theta plus theta? That's 3 theta, right? Plus I. And then the same thing happens here, but it's a sine, cosine, cosine, sine, but it's the addition identity. And it's 2 theta plus theta is 3 theta. So it's sine 3 theta, right? And there you go. And you can just see the pattern seems to be working, right? Now this isn't a proof. I'm just showing you how you can work out it a couple times, and you can see how it works. If you want to prove it, you can go ahead, and if you're savvy, you can try to prove it by induction, right? You know, which I'm sure you're anxious to do. But go ahead, you can give that a shot if you'd like, and you can prove it. But it does end up working, right? So that's what Dumois theorem is right up here, right? And let's go ahead and look at an example, right? So it says, example 8, use Dumois theorem to calculate the complex number 1/2 minus root 3, 2 to the nth power in polar form for n is equal to 1, 2, 3, all up to 12, and represent the complex numbers in the Argand diagram. So if we just let this point right here let's use this color right here. Let's let this distance be a 1. So this is the radius, right? So we can see that this complex number is a half, right? And then it goes down to root 3. That's right here, right? So this would be our z of 1 for n equals 1. So we'll call z of 1, that's for n equals 1. Our radius is 1, and our CIS, well, that angle would be a negative pi over 3, right? Good. And then if we squared it, right, well, when we square this, we'll just call it z, our second complex number. It's when we square this number. 1 squared is just 1. We're going to have CIS. Using de Moivre's theorem, it's a negative 2 pi over 3, right? Good. So negative 2 pi over 3 comes right here. That's z2. And then z3 is CIS. Now that's when I'm cubing 1. I'm not cubing this one. I'm cubing the original one. That's just going to be a negative pi, right? Right here. So I get z of 3. And then if I do z, the fourth complex number, which I'm going to get by taking it to the 4th power, it's a negative. It's going to be CIS of a negative 4 pi over 3. Right? And that's going to be right up here. So that's a z of 4. And then right here, z, the 5th complex number we have is taking to the 5th power. It's a negative 5. Wait, my bad. It should be CIS of a negative 5 pi over 3. Right? Which brings me right up to here. Right? And that's a z of 5. And then z of 6. We're taking this to the 6th power. It's CIS of a negative 2 pi. And that gets me right to here. So this point right here, 1, that's z of 6. Now they set up to 12. I think they made an error in the example. But you know what ends up happening? This is going to be this one right here would be the same thing as z of 12. I mean, I'm sorry, z of 7. Then this would be z of 8. Then this is z of 9, z of 10, z of 11, and then finally z of 12. And there you go. It just keeps wrapping around. And we could keep going, but those are the complex numbers that it keeps going around. Sound good, guys?